All right, so we're continuing this process of trying to figure out how to build a model to answer the question, can we launch a person into space? We've gotten to the point of drawing this sort of qualitative representation of what the interactions are between the person during what we think is the key phase of motion, which is the time after they've left the cannon, while they're still traveling through the atmosphere, right? And so our next step in this is going to be to try to figure out how to turn this kind of qualitative representation into something a little bit more quantitative, right? How do we actually model these forces as actual expressions that we might be able to evaluate? How do we model the position and the velocity? So how are we going to think about this more quantitatively?
Right, and I just want to capture some of the assumptions that came up from before. So one of the big things we talked about last time was that we're going to assume gravity is constant, at least for now, and consider it potentially in other iterations. Is there an impact? And we're also going to assume that mass is constant over time as well, that the person's just going to keep the same mass, they're not getting rid of any, whether it's like jackets or helmets or other things.
What are you thinking of exactly here, Alex?
Well, you know, the parachute and the cat, I'm all confused. All right, so those are just some initial things to be keeping in mind as we're moving forward. So coming back to this image right here, we are seeing that we have these two forces, and they're acting as they're vectors, so they have some direction to them and some magnitude. So if we start to think about how you might write out expressions for them, we can start with the one maybe we've used most often, so the force of gravity. So when we think of the force of gravity vector, we know that if we keep gravity constant, it's mass times gravity. But as you can see here, it's pointing in a downward direction. So we sort of need some way to indicate what is that direction. So we're going to have to determine some kind of coordinate system.
Right.
Do either of you have a preference?
Well, I mean, I love spherical coordinates, but I think for the purposes of this problem, it would probably make sense for us to stick with Cartesian. Like, Cartesian are just easier to deal with, right? So I think we should draw like a coordinate system with an x-axis and a y-axis. Like, y is height, x is distance, right? Y is equal to 0 at the surface of the Earth. That's probably going to be the easiest coordinate system for us to deal with.
All right, so I'll draw that down here. So if we think about it this way, we have a coordinate system, we have a y direction and x direction. We're at the surface of the Earth. And we have our person again, moving.
It's such a cute little person.
Thank you. Thank one of my former UOCD students. So they're at some position. So we might even kind of think about there's some position vector, r vector, that can tell us where they're located, and they're moving at some velocity. Okay, so we have this coordinate system, and if we think about the fact that the force is acting in the downward direction, it's actually acting, so the force of gravity vector is negative, in the negative j hat direction.
Right, so I hat is a unit vector that points in the x direction, and j hat is a unit vector that points in the y direction. And a unit vector just means a vector that has length of 1, no units associated with it, it's dimensionless, so it just tells us what the direction is. So it's minus mg it's mg in the down direction.
Right.
Okay.
So now let's look at the force due to drag. So here what we're doing is we're really thinking about the fact that, you know, how almost in that, again from the reading, how slippery is the person traveling through the air. So if we look at the equation for drag, it looks something like this. Again, it's acting in the negative direction, and it's 1/2 times the density times a coefficient of drag, we'll talk about that in a second, cross-sectional area, as well as the actual velocity of the man. And at this point, we can see the velocity vector is pointing here, but we don't know exactly how that relates to I hat and j hat right now. So we're going to use the unit vectors again, but actually use a unit vector called v hat, which is just indicating that this is in the direction of the velocity vector.
So if I take a minute to look at that, let's just think about that a bit. So one of the things you can see here is that this force, right, is opposite the direction of the velocity, right? There's that negative sign there, and then it points in the direction that's opposite v hat, which is the direction of the velocity. Another thing you can see is here this v squared, right, says that when something starts to go faster, there's a lot more air resistance, right? It's not just that it increases with velocity, it increases with velocity squared. What's that A mean?
So the cross-sectional area is looking at how much is passing through the air in that direction. So you would almost take like a cut through the person, and
so we sort of slice them this way?
Yes.
Just figuratively speaking. I mean.
Yes, we don't want to hurt our person, remember. And
so
thinking
we sort of
about
look in there, and you can sort of see like, you know, there's the large intestine coming up and going down. Sorry, just kind of realized.
we could also think of this as our cat falling out of the building, that is cat shaped when it's first falling and then switches to flying squirrel position, and so it has a larger cross-sectional area.
So, I mean, just to sort of get some numbers around this, what do we think that A is going to be? Like, what's a value for that?
All right, so this is what happens when I start doing estimation problems at home. So I'm going to guess, just say it's about 0.05 meters squared.
Why do you say that?
I may or may not have used a tape measure to try and figure out the thing. You know, I was excited about this problem.
All right, whatever you say. All right, that's cool. 0.05. You know.
Oh, 0.5
so like if
meters
it would
squared.
be, it would be like 0.1, basically.
Fair enough. Fair enough. All right. So the next thing that, as we're going through this equation, is that coefficient of drag. So what we end up thinking about when we think about air resistance is that shape is really important, right? So it's almost like if you think about a car that is shaped like a box, doesn't necessarily have, you know, it creates more drag against it than a car that's got a really like sleek body and the air can travel across it faster. So shape becomes important. So if we think of this person going through the atmosphere, we might think of them maybe wearing a helmet to be safe. They've been launched from a cannon.
That sounds safe.
Slightly safe. So we could almost think about them in the shape of a bullet and take that coefficient of drag, which is about 0.3. And as Mark said before, this is dimensionless, so that's important as well.
All right, so I think the one other thing that we actually maybe don't know how to express right now are these V's, right? And actually the R as well. So I wonder if we should define what the position of the person is and also what the velocity of the person is with respect to our coordinate system.
So we might want to save that for the next video, though.
Okay, let's do that in the next video.